So hello, I'm Aline from University of Brasilia. Welcome to Dynamic 2021 webinar series. Today we are in the fourth day of the event. Here I have the schedule of the week. So now we'll have a special session on COVID dynamics. Today in the morning we started the first short course that was in passive vibration control. The second part of the short course will be tomorrow in the morning. And today in the afternoon, we will start the second short course in dynamics and control. And the second part of this short course will be tomorrow in the afternoon. So here have the information of the short courses. So the first one given by Professor Domingos Hadi, that started today in the morning. And the second one will be given by Professor Paulo Curca. So now I'd like to, in the name of the organizing committee, I'd like to welcome and to thank the speakers and the mediator of this special session on COVID dynamics. So Professor Americo Cunha from the State University of Rio de Janeiro, Professor Silvio Ferreira from Federal University of Viçosa, and Professor Marcelo Savi from COPPE Federal University of Rio de Janeiro. So thank you, and I hope everybody enjoyed this special session. So Marcelo, I pass to you then. Thank you.
Thank you, Aline. Hello, everyone. It's a great pleasure to be here to present this COVID dynamic session. So this is absolutely a very important topic nowadays. And so I would like to introduce both of the presenters. So Americo Cunha Jr. is from State University of Rio de Janeiro, and he is working with this modeling of epidemics in general, especially the COVID-19. And Professor Silvio will present in the sequence. So please, Americo.
Well, thank you for the introduction, Marcelo. I wish to thank also the organizing committee for the invitation. It's a great pleasure to have the opportunity to present here part of the work we have been doing in epidemic modeling in the last 4 years, okay? We didn't start this with COVID, we started in fact with Zika modeling, but gradually our interest migrated to COVID last year. So let me move to the slides. Can you see the slides? Marcelo, are the slides appearing?
Yes.
Okay. So we moved to COVID last year, but today what I wanted to present to you is not so specific regarding what our research group is doing, but as the audience of this conference, I believe most of the audience is not familiarized with the fundamental aspects of modeling of epidemic outbreak. I will try to give you a general overview, what kind of approaches can be done. Okay, maybe in the comments in the comment section, I can give more details about our group work, okay? So this is done in collaboration with Michel Tozin, my master student, and many other collaborators. I wish to motivate this talk. We're presenting a real situation here. You can see in this slide some information regarding two real diseases, disease A and disease B. The case fatality rate for the first disease is around 40%, and it is transmitted by body fluids. On the other side, the disease B has a much smaller case fatality rate, around 0.01%, but it is transmitted by respiratory droplets. I wish to ask you a question. After 1 year, which disease will kill more people? Think for a moment, and please put your answer in the chat, okay? And Marcelo, I kindly ask you, as I'm not seeing the chat, you can tell me what answers people are putting, more A or more B. What do you have more, A or B?
No.
We don't have. So Marcelo, what do you think? Disease A or disease B?
Oh, I think droplets, probably.
Okay, probably. On the contrary, I will not put this slide here. Okay, good guess. The first disease is Ebola. The second one is the swine flu, H1N1. Okay. The biggest outbreak of Ebola took place in Western Africa from 2013 to 2016. It infected between 30 to 48,000 people and killed around 11,000 people. Okay. The swine flu took place between 2009 and 2010, 1 year. And during this year, it infected between 700 and 400 million people, and killed. The estimates of deaths associated with this disease is between 150 to 575,000 people. Okay. The key message here is infectivity may be much more dangerous than virulence, okay? And flu-like diseases are the major threat to public health in this sense. So we're seeing this situation regarding COVID-19, it is in the family of the second disease, okay? These flu-like diseases are very dangerous. Concerning the global aspect, for a population, they're very, despite they're not so dangerous from the individual perspective, from the collective perspective, they are a major threat. What I want to present today is how to deal with this kind of infectious disease modeling, especially. So our perspective here is to see a mathematical model as a machine, something that receives raw material, process it in some way, and return a processed product. And our machine here is a mathematical model. It receives some information about the disease, process this information according to a certain set of equations, and give you a prediction as the final product, okay? And the approaches I wanted to give you an overview today are collected here. I wanted to talk about 5 possible ways to model the spread of an epidemic: statistical model, agent-based model, compartmental models, multi-scale models, and graphic models. Let's start with the simple approach, the statistical models, okay? Here, what we are interested in is to compute with a certain level of accuracy numbers of the epidemics. For instance, the number of infected people or the number of deaths associated with the disease, okay? And you can see here 2 possible approaches, 2 statistical regressors, one constructed by our group of surveillance monitoring, the COVID-19 Fluminense Observatory, and this is from our friends from COVID-19 Analytics, okay? There are 2 simple, you can see both are simple approaches, okay? This kind of equations are very simple, they have, because of this simplicity especially, and because the data, at least trivially, don't give you so much information to predict the future for long term, these approaches are limited to produce accurate predictions for a time window that spans between a few days to a maximum 1-2 weeks, okay? So you can't do better predictions than an horizon of 10 days, 14 days with this kind of approach. But it's very useful to predicting the short term the statistics. For instance, how many deaths are we expecting for tomorrow? How many new cases? Okay. The fundamental reason, because these 2 types of model, these 2 models don't have a lot of prediction capability, it's because they don't have inside their structure a mechanicist structure, okay? They are just curve-fitting approaches. So if you wanted to predict this kind of behavior with more fidelity, to the reality, we need to introduce some mechanicist structure. And this, in this sense, come first the agent-based models. You can see here illustration. We have some agents here moving. Okay, they follow a certain dynamic evolution law, and you can see that the color of the agents are changing. They started blue. Okay, I will restart here. They started blue, and after some time, some of them become red. They're infected, and they change color again to represent they are recovered from the disease. And what we can see here is that as they are moving and interacting each other, they are transmitting the disease. In this second video I'm showing here, we blocked the movement of 90% of the agents, okay? Only 10% of the agents are moving, and you can see a drastically reduction in the transmission events, okay? So this kind of model can give you a very important message. Social movement act in favor of the disease transmission. If you block the movement, you can reduce the transmission. In my view, this kind of models, between the mechanicist models, they are the most fundamental because they consider discrete events. The transmission, in a sense, is a discrete event. It occurs when you have people interacting each other directly or indirectly, like transmitting the transmission from one individual to another, maybe by a contact of a infected surface. But the fundamental nature of these dynamics is discrete. But as you can imagine, for the context of a big city and with a very complex dynamics, with a lot of heterogeneity, it's extremely hard and almost impossible to construct a fidedignos model with this approach, okay? So from the statistic mechanics, you can derive simpler models from this, taking some kind of special averages, and in this sense emerge the third class of models I wanted to discuss, the compartmental models. Okay, the compartmental models, you can see two flavors of compartmental models here. The first one is this SIR, and the second one is SEIR plus CAQH. What is the major characteristic of this kind of model? They split the population of the region of interest in groups, okay? They associate a label to each individual, okay? And an individual has at a certain instant of time, an individual has only one label, okay? The SIR classify people in susceptible, infected, and removed. The removed lumps the recovered people and the deaf people, okay? But you can construct more complex models like this one here. Susceptible, exposed, you're considering people exposed to the disease that are not presenting symptoms yet. Then they evolve to a state where they present symptoms or they are infected asymptomatic, okay? And you can think that symptomatic can be put in quarantine when they're detected. These people quarantined can evolve to a removed, a recovered situation, or a hospitalized situation, and the hospitalized can evolve to ICU situation, okay? All people in these compartments here may pass away or may recover, okay? And you can also consider an additional compartment of people who are confined, okay? So with creativity and driven by the necessity, you can create much more categories of models like this. But what's the problem? Why not create a supermodel? Any additional compartment that you put here associated to this arrow, you have one or more parameters. And as more complex as your model, more information you need to work with this model, because it will be much more difficult to work with this model than this one, because you have much more parameters here that you need to adjust in order to do quantitative and qualitative predictions. I will give you a brief overview of the equations, the system of equations associated with the SIR model. The equations of this kind of model are deduced by a kind of population balance, okay? you know that the population inside this compartment, its rate of change is the derivative of S. And it's changing essentially because people are becoming infected. So people are leaving susceptible compartment through infection and enter the infected the compartment. Okay, you can see here a negative sign because the population here is reducing. And this rate of transmission here is proportional to the size of the population of susceptible and infected. Okay, this cross term represents their interaction, and you have a certain constant of proportionality here, which is the transmission rate. The same amount of people that leaves this compartment enter in this one. So you have in the balance of the infected population, an entering term which is equal to the term that leaves this compartment, and you have another one leaving, moving from this compartment to this one, which is proportional to the population in this compartment. And to fulfill the balance, okay, you have this quantity entering in here. If you integrate these equations, you have this kind of a response here: in blue, susceptible; in red, infected; and in green, recovered. You can see that the population, if in the beginning of epidemic outbreak, the full population, except by a small quantity of individuals, are infected, you can see that the response predicted is the susceptible population decrease as well as the infected population increase, but the infected population increase up to a certain limit. After a certain threshold is achieved, it starts to decrease, okay? And you see a continuous increase in the recovered population. This threshold here is defined by a certain quantity, which is called the basic reproduction number, which is defined as the rate of transmission, is the ratio between rate of transmission and rate of recovery, okay? This is the famous herd immunity limit. After your dynamic system cross this limit, okay, after you cross this limit, the number of susceptible people is so small that it's more likely infected people interact with other people that are or infected or recovered and has antibodies. So the number of new infections will decrease drastically, so that after a certain time, the epidemic disappears. I wanted to show a kind of parametric analysis now, changing the reproduction number. Here's 5. What you see when I reduce it? The drop in the susceptible reduces its rate as well as the increase in the infected, okay? In the first situation, almost all the population recovered from the disease. Almost all the population was infected. But in this last scenario, you can see a significant part of the population that was not infected, which corresponds to this susceptible in the end. So in some sense, you still have wood to fire here in this situation, where in the first situation, all the wood was fired, okay? I want to emphasize here the qualitative aspect of this kind of approach. In my view, is much more important the qualitative information that you can retrieve from this kind of model than the quantitative one. You can see that decreasing the reproduction number, you decrease the peak of the outbreak. This is the famous flatten the curve, okay? And how do we act on this, okay? To decrease the R0, we needed to decrease the transmission rate. And the transmission rate beta, you can see here 3 situations with high, medium, and low values, okay? Reducing the transmission rate, you can save, for instance, your health system from the collapse. So this is a qualitative information that was obtained by the experts from this kind of simulation, okay? I wanted to show another situation here. I included a new compartment of confined people here. So this is a SIR model with confinement. Here are the equations. If we simulate this without any confinement rate, the response is equal to the SIR model. But if I include a period of confinement, okay, we're including here 90 days of confinement, what you can see here, the confined population increases. With the increase of confined population, you can see a giant drop in the susceptible population. But this giant drop has nothing to do with the infections. It's more related, it's not only because of infections, it's more related with the confinement of the population. The people became confined, so they're protected from the infection, okay? After a certain time, you see some people leaving because their patience is over, so they started to leave the quarantine, the confinement, okay? And here in this point, the government turned off the confinement period. Some people are still afraid, but after some time, people start to leave. What you can see, the increasing in the susceptible population again, and with this susceptible increase is followed by an emergent new cycle of infections. This is what's popular known as second wave. So what you can see here, the second wave we are observing in many cities here is a direct effect of the confinement period, because during the confinement, you protected some people, which if you were not protected, perhaps will be infected in the first wave. So they are infected now, but in some sense, we are reducing the expenses. We are having a smaller number of total infections, splitting these infection cycles in many waves than if we leave all of the population being infected just once. Possible improvements, these models I just show are purely temporal, but you can include special dependence. This is a very recent work done by my friends Malu Grave and Álvaro Coutinho and some collaborators, and they included some space operators here. They construct a kind of reaction diffusion SIR model, and they applied this for Rio de Janeiro scenario, okay? And they could construct a simulation which reasonably well described the epidemic wave in Rio de Janeiro, okay? But both approaches, the purely temporal or this special dependent one, their range of applicability is very limited because you have a very strong hypothesis behind this kind of approach. Homogeneous population, okay? So if you wanted to apply this kind of approach for a big country like Brazil, you needed to move for another approach, much more complex, but much more powerful. And this is the subject of the talk of my friend Silvio that will be after mine. Just to give an idea, this kind of meta-population model consider each city in the country as a SIR-like model, like those one, and the different cities exchange population according to the flux of people, because some people move from one city to another every day to work and return back. This flux of people increase the influence a lot the epidemic. So if you wanted to capture this kind of effect in a giant region like a continent-like country as Brazil is, you need to include this transport information in your model, and the strategy is using this kind of multi-scale model. Okay, Silvio will give more details. To close the talk, I wish to talk about one last approach, which we call graphical model. Some people may not consider this a model, but we are going to consider in the following sense: a model receives some information and give you a prediction, and this is what this type of graph do. It receives information and return to you some kind of prediction. It give you a measure of tendency. Okay, you can see every day in the news this kind of graph showing the incidence as function of the time. You can obtain some kind of information here, but this is not the most informative graphical model that you may have. If you put inside the number of new cases as function of the number of total cases in a log-log graph, I affirm to you that this is much more informative. Why? In the beginning, the epidemics is exponential. When you move to log-log scale, an exponential curve, it is transformed in a straight line. So in this kind of graph, you can see the exponential phase of the epidemic as a straight line. And when you leave the exponential phase, the number of new cases decreases a lot. so that when it's divided by the total one, you're going to have a small number. And you can see the drop, the leaving of the exponential phase here, and when you enter in the extinction phase here, okay? This kind of graph is much more informative to inform you in which step of the epidemic you are than the previous one, just showing a time series, okay? And the same idea can be translated to a heat map, which is a kind of thermometer. Okay, you can see here let's see, Rio de Janeiro state here. Okay, you may see it was okay, but passed a hot season. Okay, a period of a lot of infection that decreased and then increased again, decrease and increase. Okay. This kind of model, graphical model, is very useful, especially for people not trained to read this kind of information. Okay. Just an alert: mathematical models are powerful, but they have limitations. What kind of limitation we have here in epidemic modeling? We may have the use of an inappropriated model to a certain situation. Okay, try to use a statistical model to predict the future several months ahead. This is completely nonsense. Okay, this is like if your model, if you think your model is a machine, this is a situation like use a defective machine. And your raw material may be of low quality too. Your data may be of low quality. And in this scenario, if you put a low quality material in a machine, or perhaps your prediction will be, your final product will be of low quality. So poor data, very, very poor data lead to very, very poor predictions too. Okay. So key messages: models for epidemics are powerful, but should be used carefully, especially because this is a very interdisciplinary areas. To interpret correctly the results, it's a multidisciplinary task and should be done by a team of specialists with different areas of expertise, not only by a single person, okay? If you are interested in learning a little bit more about this, we developed in the COVID-19 Fluminense Observatory an educational code with very pedagogical tutorials. So if you're interested, you can download our code in this website. Okay, you know, you pick the address in this QR code. I wish to thank again the organizing committee for the invitation and also the collaboration with these groups of work and the financial support of the agencies. I acknowledge your attention, and if you have questions after Silvio's talk, I'll be happy to answer. Thank you.
So thank you, Americo, for your nice presentation. It would be nice if our decision making can take a look at that, but unfortunately, it's not the case here. So let's move to the next presentation. So this will be presented by Professor Silvio from Federal University of Viçosa. And Professor Silvio works with complex systems in general, including the epidemics model. So let's pass the word for him. Thank you very much.
Thank you. I thank the organizer for this nice invitation. I gave a lot of talks last year about my work about COVID-19, but this is the first time that I'm talking for audience different from physicists. So it's a pleasure to be here. So let me move to my. Let me start with telling a little bit about my collaborators. Actually, all the results that I'm going to show here was done by these guys. This is Artur, is a master student. He's working with some modeling for vaccination. And Guilherme and Wesley. Wesley is now a postdoc researcher here in Viçosa, but he was my former PhD student. And Guilherme is still in the PhD. He's concluding his work in the next month. And they did all the work. So let me introduce a bit about my group, because Viçosa is better known in Brazil by his contributions for the agricultural science, but we also do nice physics there. And here is everyone who is working with me. This picture is the old picture before the pandemics. So we have to update it carefully because, for example, Hugo was not with us before the pandemics, but he's now with us, and Laura has just became a member of our group. Here are Guilherme, Wesley, and Artur, who is the main guys of this work. But there are other students, and Diogo is also an alumni of our group because he finished the PhD last December, but he's still working with us. So let me give you a brief overview of my talk. Actually, my talk is much larger than the time that I have, but maybe I can talk quickly about these different points. But I do a very brief introduction because I take the advantage of the previous talk of Americo that helped me a lot. And I will explain a bit about the work that we published last year about this meta-population model for predicted epidemics in Brazil. And then we will also present some things that we are developing right now. For example, a data-driven model for vaccination. I will try to make you familiar with this term, data-driven, along my talk. And finally, if I have time, I will do some quick concluding remarks. So just to remember the worldwide situation of COVID-19, here we can see clearly the second wave in many countries. Here in South America, we don't have clearly a second wave because actually we never had the pandemics under control in South America. Brazil is not different. But in Europe, you can see clearly that you have the first peak with a lot of infections per day, and then a second peak, even higher than the first one, as Americo explained in his talk, the same for the United States. And but not here for South America. America, we are in the plateau for many months. So the pandemic was never under control here in South America. Just a very quick review about the biology or the infection steps of a disease like coronavirus disease is not different from other viral respiratory virus transmission. We have a susceptible phase where you don't have the virus in your body, and then you have an exposure period where you don't have any kind of symptoms or transmitted disease. There is a time window where you are transmitted disease, and after this, your immune response start to work very effectively, and the level of the pathogen in your body is low, and then you can be in a recovery state. You're not transmitting anymore. But in the case of COVID, there is a danger interval when you have no symptoms, because this above line is the medical, the clinical state. You have an incubation period when you're not sick, and you have a period when you're sick. So this short time window is the danger one in the case of COVID-19, because you move around without any care, and you can transmit the disease without any kind of control. So this is a very important property of the COVID-19 disease. So Americo explained this briefly, so I will repeat very quickly here. This basic reproduction number, it says you how many new infections will arise when you introduce a single infected individual in the population. So for several diseases, they are different. For example, for measles, it's about 16, while for COVID, it is about between 2 and 3. So it's important to remember. If this number is below 1, you have an epidemic which is under control. If it's above 1, it's not under control. And the higher this value, more dangerous is the situation. Another concept that I will reinforce to you is the concept of herd immunity. Americo explained a situation when you can reach herd immunity through the natural evolution of the disease, but actually it's hardly to be achieved because the disease undergoes mutations. The virus will adapt and it will reinfect people. So it's much more complicated to reach some herd immunity naturally. So you have to use vaccines. vaccines. So here we have an idea when you have a few persons who are protected, the epidemics will evolve, will infect a lot of people. But you have too many people who are immunized through vaccination, for example. Only a few individuals will acquire the diseases, so you don't have a problem with the disease. It varies a lot about different disease. For example, for COVID-19, there is an estimated between 50 and 80% of people has to be immunized to achieve this herd immunity. So here is a summary of some properties of COVID-19 that I will discuss in my work. But I would like to pay attention only in this one, when you say that herd immunity is about 50 to 80%. So there is a preprint that was posted in September in 2020, when they claimed herd immunity in Amazon, more specifically in Manaus. Is a work done by various good scientists, Brazilian scientists. And they published this work in last January, but they changed the title because Manaus had not achieved the herd immunity yet, because you have the problems of the mutations. You have the variant of the Manaus that everyone is worried about it, and you have a second outbreak of COVID-19 in Manaus in the last months, and it was a big problem. So herd immunity is a very complex issue, even though the epidemic models predict herd immunity. Actually, in practice, you will achieve herd immunity only through vaccinations, because the virus will adapt and will reinfect people. So vaccination is the only alternative to contain the virus, like COVID-19. Okay, now we'll change. You skip to discuss our approach of data-driven model. The idea of data-driven models is that you have models that are very complicated with too many parameters, but these parameters are mined from the literature or for some data sets. The idea, you don't have to control all the parameters. You have only a few parameters that you can change and to test your model. So this is the data-driven approach. You have too many inputs in your modeling and a few parameters that you can control it. So I will tell you quickly about our work, but there is a huge explosion of works telling about COVID-19 dynamics using epidemic modeling, models like these that I will describe for you today, and the others like those that Americo explained to us, including one that's highlighted in red, that is from a group from Brazil, a very nice paper. This is only the publications in sizing for the first 3 months of the COVID-19. So it was a very active field of research. And this was our contribution. We did something more in the framework of generic predictions without specific predictions for a specific place. So I will tell a bit about this work for you today. So the model is in the line which Americo explained to us. You have several populations in this study because they are dynamic cities, and within each population we have a mixing hypothesis. It means that everyone can have
Hello, everyone. I think we had problems with the connection. I don't know if it's for everybody, but I believe so. So let's think about the solution. maybe we can go through some answers to Americo to start to answer some questions. So let's wait for the Silvio reconnection, but maybe Americo can answer some of the questions. So Americo, can you see the questions?
Yeah.
So let's start with the Adriano
questions. Okay.
So
Thanks
please.
for the presentation. How do you see the application of machine learning to artificial intelligence approach for disease modeling like COVID? Thank you for the question, Adriano. Machine learning it's another kind of tool here. Okay, it has potential to add, especially in the calibration of very complex models, but it's not the definitely tool, the game changer. Okay. In this kind of complex system, you have many different approaches and they're complementary in some sense. Okay, those agent-based models, as they consider the discrete nature, for instance, they can be used to understand some particular details of a very specific region. For instance, let's say we want to see the effect of the breaking time in transmission inside schools. You can use those kind of that kind of model to emulate a typical situation in a school and see the effect. Okay, and machine learning tools may be very useful to calibrate, to infer some information from the boundaries to inside the domain. But let's say we want to understand the situation in the whole Brazil. An agent-based model in this situation is useless. Those kind of meta population that Silvio presented is much more suitable. Machine learning is essential in this case to solve the inverse problem, to calibrate the model with the information of infection that you have. Okay, machine learning approaches for this scenario are very nice. But and use as a black box, let's say, you can use it also for time series prediction. You can calibrate a neural net to give you an estimation of the number of infected and the number of deaths, expected deaths for a few days or a few weeks ahead. But I don't know yet any approach using machine learning to try to mimic the mechanics of the infection. Okay, I think from now this is the context of machine learning inside COVID.
Okay, Americo. So the second question is from Professor Katarina Pavlovskaya. She's asking about a comment on the choice of parameters and validation as well.
Very nice. It's extremely difficult to choose the parameters there. Now we have 1 year of infection. Now we have some knowledge of the parameters. You have a lot of papers, careful done papers, which they store this information. But in the beginning, it was a pain in the neck because you didn't have. So we saw many people of experts and non-experts trying to calibrate those models. Okay, you can do this from time series. We did, but we didn't publish. We did it for ourselves. Because you calibrate, as we do, we mechanicists do with a vibrating system. We calibrate with the data, okay, and we try to do predictions for other situations, and we compare with experiments. Okay, they agree, the model is validated, you can use. You're happy with this. What's the problem here? Those models like the SIR, they have some kind of mechanicist relationship embedded in their structure. But there is a extremely important ingredient they miss. The rate of transmission, that beta in the model, depends on the behavior of the public. Depends a lot on the social behavior. And in the format I showed here, those models don't take care of the social behavior variable. So what happens if you calibrate this kind of model and try to predict the behavior, let's say 1 month ahead with this? You're going to make a wrong prediction. You calibrate your model, okay, the prediction, and you started to use it to predict a few days, a few weeks ahead. In the beginning, okay, they'll follow close trajectories, but after some time, the reality take one path, and the path that the model takes is a completely different one. And last year, in the Proceedings of the National Academy of Science, a group of physicists published an explanation very interesting to this. This is not a chaotic system, okay, but it suffers from the lack of predictability, a lack of predictability mechanism that's comparable to chaotic systems. It's impossible you predict for this kind of system the behavior much ahead, okay? And in a sense, the reason is the social behavior affects, the course of the epidemics affected the social behavior, and the social behavior affected the rate of transmission. You have a kind of realimentation here, which is not taken into account in those mechanicist models, okay? So calibration validation here can be done in the classical way we do in mechanics, but you need to be aware that you need to recalibrate your model every week, okay? Your horizon of prediction is very short, 10 days maximum, with that kind of compartmental model. After 10 days, you need to recalibrate your model and go on, go on, go on. It's a good point to... our group started to work with this when we did the same take with Zika 4 years ago. So that this time we were vaccinated against this, but I saw many colleagues with the best of the intentions trying to do this and completely over-predict or under-predict the reality, trying to extrapolate predictions. I saw a colleague once doing a prediction 6 months ahead and trying to say, oh, the peak of the epidemic will be this day. For this kind of system, predictions, long-term predictions, must not be interpreted in this sense. Okay, in the beginning of this year, I participated in a seminar organized by Amorim University in the United States with a group of experts, and this was one of the major conclusions there in this seminar. Predictions here must be understood different from predictions in other areas like physics, engineering, where you can make the high fidelity predictions. You can't do high fidelity predictions here. You need to draw some scenarios, or observe some scenarios, and some limit scenarios. Your predictions must be inside an envelope defined by different scenarios, a best case and a worst case. I don't know if I did I answer your question?
I think so. Americo, another question here is, can you see here from Eduardo Reis? How did you derive the reproduction number R0 that is given by the ratio beta gamma?
Thank you for the question, Eduardo. It's an important point. First, what's the R0? The formal definition. R0 is the number of secondary cases expected from the first infection. You have the first individuals, the patient 0, which arrived in a city and started to spread the disease. R0 is the number of secondary cases you expected from this first one. But this R0 is a kind of it's a kind of bifurcation parameter in this system. How can you derive it? The formal approach, you have different expressions for R0 for different models. For SIR is one expression, for SEIR is another one, and for that model I presented, that complex model I presented there with many compartments is a different expression. You have a general strategy known as next generation matrix. you computed the matrix, you construct some matrices with the flux of exchange of people from one compartment to the others, okay? You compute the product of one of these matrices with the inverse of the other one, and you take the spectrum. The biggest eigenvalue is the R0, okay? But for people here from mechanics, I can give you for SI model a simpler approach. You transform your equation, you put your equations in dimensionless form, and the R0 will emerge as the dimensionless group of that equation, okay? So if you put your equation in the dimensionless form, the dimensionless group you're going to have for that equation is the R0, beta over gamma.
Okay, Americo. So now we have another question, but now I think Silvio is back. So this is to show the unpredictability of our reality. And so Silvio, you are back. So
Sorry, actually, I have no idea for how long I speak to myself because the student started to send me messages, but my cell phone was turned off. I have no idea where I stopped.
Okay, but so you were talking about let's see your slides, but you are showing the situation what one person passing to another. So there is a round picture with some people there, and so
let me share again the seminar. Share screen. Okay. Chrome tab. Okay.
So then you can include this in your presentation, right? The unpredictability. So before that, yeah. This paper you show it. Okay. So yeah, I think here is a good point to restart.
Okay. So let me try to. Actually, let me tell what's happening. My two kids start to have class, so I'm afraid that it will be very unstable from now on. But let's try to do this. You keep the eyes in this connection to know if you are connected or not. So I skip all the introductions and tell quickly about the model. So the meta-population model, Americo already explained to us the idea. You have cities and mobility from one city to other, and this mobility is very important for the transmissibility of the disease. And within a given population, for example, city, we run a compartmental model, like the ones that Americo explained pretty well. So this is the contribution that we did first. We published this paper in the end of last year, December, but we started working in March. It was ready around April, so it took a long to be published. So we use a data-driven approach because this kind of model, they have many parameters. So you have to import this parameter for some database. You cannot play with all these parameters at the same time. We have thousands of parameters. So what we call of data-driven approach. You have the data, and you introduce this huge amount of data in your model. You have only a few parameters then that you can change. So this is the mobility network that we used. So here we have different cities, and the wires are the connection among them. Here is, for example, one example of the number of a distribution of seats in which at least P% people move to another seat every day to work or to study. This number is not negligible. It's 2-3%. You have outliers with 15% or more. So it's very important. Here is another important data that you have to introduce in our simulations, in our models, is the amount of people that are infected already. So it's we try to infer this from reported cases. It's not so simple because actually the people who are detected, that does not represent exactly the who actually is infectious. So you have many underreported cases that are also important for the epidemic spread. So let me move a bit quickly. We use this type of data to set the initial condition. For example, we use the number of confirmed cases to build some initial conditions, but I will explain in the end of my talk if I have time. Actually, I don't have time anymore. But in the first study, we just used the input at the beginning to start the simulations. We must pay attention that this kind of model is very important when we are in the beginning of the pandemics, when we start to spreading, where most of the cities does not have yet confirmed the cases. So it's very important to draw some strategies. So, but now where every city has sustained transmission, the mobility is not so important as it was in the beginning, but it's important. So let me show you two moves very quickly. We can see these moves in the YouTube that Wesley made them available. So you can see here two hypothetical scenarios for the pandemics, where we have in the left side what we call a weak mitigation. So you can see the wave of infection start from the coast and move towards the countryside. And if you have a moderate mitigation, this process is much slower. So it's very important, this kind of modeling, when you are starting epidemics like this, because you can, I would say, prepare yourself better. For example, while the pandemics is increasing hugely in the big cities, in the small cities, they are not so strong yet. But of course, now we know that every city in Brazil having problems with COVID-19. But in the beginning, it was a very interesting contribution. One of the nice discoveries that we made is that if you look for the epidemic curves in different scales, for example, states or cities or other geographical classifications, for example, what IBGE calls intermediary regions, you can see that the epidemic curves varies a lot from one place to another place in the same country. So to be very briefly, the message here that there is not a single pandemic in a country like Brazil. You have several manifestations of this same epidemic process, each place with its particularities. So it's very important to take local measures, not only the global ones. Just one example that we could investigate is the correlation between some epidemic parameters. For example, the time when the peak would happen if nothing different happened, in relation to the distance of the capital city of each state. So you can see, for example, in São Paulo, that the further you are from the capital, the slower or the longer the epidemic peak would happen. It means that, okay, the epidemics will delay more if you are further from the capital. But if you look, for example, for Paraná, there is no correlation. It seems that the epidemics there happened at the same time in several foci, and in the end, there is no correlation with Curitiba. In Minas Gerais, we have a mixing. For short distance, we have no correlation, but for long distance, we have correlations. So we can do this kind of predictions with these meta population models. If I have more 5 minutes, I would skills a bit about vaccination. Do I have?
Yeah, go ahead, please.
Okay. Let me go. Oh, so let me tell very quickly about vaccination, because maybe it's the most important issue that we have now about COVID-19. So here, just for sake of illustration, I am showing the vaccination per capita for different countries. We see that Israel is very, very ahead. Everyone. United States is also quite well. Brazil, not too much. We have a tiny amount of people vaccinated. There are many other countries that are above Brazil, but I show only a few ones. You can see that India, for example, is not caring about vaccination of his all people. Actually, India is a huge country. It is very complicated to vaccinate everyone. Huge population. But you can see that our current vaccination is really low compared to other countries. So it's a big problem. I will show you some reasons to believe this. And now, considering more specifically Brazil, we can have some data. Yeah, you can see in Brazil we are vaccinating in a very 200,000 people a day. We were vaccinated, and it seems to be a lot, but it's not. It's really little. I will show you some predictions based on these numbers, but it's actually, I can do the data-driven approach also for investigating active vaccination, because these data are available. For example, you can see this in the same web page that I mentioned. I don't know if I mentioned that when I was offline or when I was online, but you can see this in this website that that Wesley organized. Here is the kind of simple model for vaccination, because actually it's not simple at all, because we have the same model that we use for meta population. That's relatively simple, but we introduce now the vaccination, and there is some delays, because when you take the vaccine, you're not immediately, and you have the chance of not being immunized. And so we consider all these features in this model. So we have a simple model for epidemic transmission. You have susceptible, who gets in contact with infectious and become exposed, then they evolve to asymptomatic, can be recovered, and or they can be really asymptomatic and can go to death, or it can be vaccinated and become immunized or not. So in this case here, we have the vaccination. We vaccinate all the groups. In principle, we have parameters for each one, but we assume that all the groups are vaccinated with the same rate. And you can go to any state that they are immunized, when they're really vaccinated, for example, or you can just be vaccinated but not be immunized. Okay. In any case, you can evolve to an state where you are immunized, because you can get the disease and be immunized. So it's a bit complicated model, but we still split it in 3 groups. Maybe we should split in more groups, but in 3 it's complicated enough. We divide in invulnerable, that people that had age above 60, the adults that with age about 19 and 60, and the youth people that they are the young, that are not in principle they will not be vaccinated in this beginning. So we can try, we can make tests, we can make hypotheses, we can simulate hypothetical scenarios using this type of modeling, just to have you an idea how complicated it can be. This is the model for this is the set of equations for one population. You have to multiply this for the number of populations. In our case, there are 3 populations. Here we're not using the meta population approach anymore. It's just for one population. And here is the continuation of the model. So you have 16 equations times 3. You have 48 equations. So of course you cannot use change this parameter. So you have to use the data-driven approach, where you have to mine the parameters from some sources. Fortunately, we can obtain the contacted parameters, because there is a very nice work that everyone is using in COVID-19, when we have the average connections an infection contact. These contacts are divided in groups, in different groups. For example, you have kids in the school, kids in the home, kids in other environments, and the same for elders, and the same for adults. So it's a very interesting work. So we can compute this contact matrix. This contact matrix means that, for example, group 1, that are the vulnerable, they have 10% of their contacts is from people from group 1, 60% is with adults, and 30% is with kids. And this is the situation where we exclude the classes. We exclude the classes. Kids are not going to the school. But if you include the school, the situation will become a bit quite worse. For example, you have the divergent connectivity of a kid that it's not in school, it's about 13. If the kid go to school, it raises to 19. This contact matrix changes a lot. So we are using again the data-driven approach. So here's some parameters. I'm not discussing this very carefully here, but you have to you fix most of the parameters based on data that you mine in different places, and then we use a single control parameter that we call R22. Is essentially the reproductive number if only the adults were living normally, was having a normal life. Yeah, if you if you neglect the infection of elders and kids, you can calculate it analytically for the model without vaccination. This is the parameter that we use. But of course, the infection in the adult population also influences the kid population, the young population, and the elder population, the vulnerable population. So let me show you quickly some results. And here is the typical result of the simulation. The dashed lines are when you introduce a vaccination. This number is more or less the vaccination rate. The fraction of vaccinated people per day is close to the Brazilian current rate. We are considering that people are being vaccinated with vaccine that has 50% of efficiency for infection and 100% of efficiency against. So we are simulating for the coronavac, but we can do for other vaccines if you want. And here we can see, you should not care about the absolute values here because it's a model with a lot of hypotheses, but you can see a big drop in the number of deaths. That's the important parameter. Here it drops from 3% to less than 1%. It's a big drop. The number 3% is really large. It's because the model is too simple. But here we are simulating in a situation when the R is slightly above 1. Okay, 1.2 is not slightly above, it's quite above, but it's more or less the current situation. It's not very different from this. And I'm sorry, here is for 1.9. If you increase this, but now immunizing adult first is a strategy that some people are defending. Okay, the vulnerable can wait. There is some research, important research that's saying the vulnerable can wait. So here we test it. We let us vaccinate the adult first, and we see that at least for these parameters, things are not very different when you vaccinate the vulnerable first. But if you should take this more carefully. That is actually the result that I would like to show you. This next one. So here we have some heat map. And here is the vaccination rate, and his is basically the reproductive number of the most infectious population. That in this situation are the adults. Okay, so if you vaccinate the vulnerable first, you see that the blue here means black means that nobody dies or only very little people dies, and the blue means that you reduce significantly the death rate. So you can say if you vaccinate vulnerable first, you see that is much more efficient for reducing the number of deaths. But you must be a bit careful about this, because actually, if you compare for the same region, you can see here that for this region, if you vaccinate the vulnerable later, it seems to be better. So let's compare, let's take the difference about these two heat maps, and you have interesting result. So the question is, who should be vaccinated first? And here we have a nice response. Here, if you have an uncontrolled epidemics, if you have a large reproduction number, you should vaccinate vulnerable first, because the epidemics is expanded too fast, and a lot of people will die, and the people are most of them are in the vulnerable group. But if you have an epidemics that is under control, that's in this case, it can be more efficient if you vaccinate those that are not vulnerable. But you must have an epidemics under control. Is a very important issue. And the most interesting is that if you increase the vaccination rate, you increase the region where the vaccination is very efficient, when you can drop the death more and more and more. So this is a very complex scenario that we should take very carefully. You can extract this kind of message from this model. I had a third part to discuss, but I will skip, because this is how can you do nowcasting and more forecasting for a short period using data, more or less in the sense that Americo told us, but I will skip to my conclusions. So we have some positive points in this kind of modeling approach. For example, if you use meta populations, you can investigate several places at the same time, and it's very interesting because you can draw some strategies for different places. You can obtain very important sites, even if these sites are qualitative. They are very important. It can help you to adopt some strategies or some other. You can extend this model and make this model much better if data are available, and the limitations are the same that Americo mentioned. That okay, you have problems with data. We still have strong hypothesis. For example, an in-field hypothesis that everyone has contact with everyone with the same probability. So the model has to be improved every time, but it can be very useful if you are looking for some strategies for the best insight. And that's all. Okay, sorry for the confusion with the internet connection. I hope you could hear me better this time.
Silvio, thank you for a nice presentation. So let's move to some questions here. We have a question. I think you can handle this. Can you see the question there? So it's from Dimitri.
Yeah, the question from
Dimitri. Yes, the last one.
Okay.
Do you make any predictions if the removed population entered the susceptible population after a time? So
yeah, it's a very good point. It's a very good point because actually we are investigating exactly this problem when the vaccination started in Brazil. So we have to stop this problem and go back to the problem and change our efforts to the problem of vaccination. But we are investigating this effect. What you see is the second wave. It's not a novelty in epidemic modeling. If you have a lag very long, has this 1.5 months, that's more or less estimated, you will see a second wave. But in principle, if you don't have new variations, is the case of the Manaus one, you have immunization. But we are investigating not in these results that I presented, and you will see different waves.
Okay, so there is a second part of the question here. Can you see?
The second point is the countryside may be a buffer for start the second wave on the city centers. Actually, not, because okay, it can be a source of second wave if you have a new variant in the countryside. But actually, the variant will arise when you have more and more infection. So you have, for example, some countryside when they have no control, everyone gets the disease, you wait for the herd immunity, probably you have new variants in this kind of new viruses. It's like flu. Flu every year you have a new kind of a new mutation, and you can get sick again. So in this sense, but it's more probable that the second waves will start within the same population, because you have more infections. Infections are more numerous where they start first. For example, in Manaus, as happened in Brazil.
Okay, another question is from Marcelo. So can you estimate the future of the pandemic from your model? Can you consider in your model the vaccinate? So the answer, I think it's yes, because you showed the vaccination, but can you comment the question there?
Yes, actually, I think that Americo responded this question in his talk. We can do a lot of predictions, but we are very limited by the current situation. I can do predictions assuming, okay, I have the situation right now, and the situation will stay forever. I can do predictions for long times. Otherwise, I can do prediction only for the next few weeks. So the models allow you to make any kind of prediction, but you must be very, very careful about this. So the point that Americo raised is the central point. You can do prediction for a couple of weeks, maybe 1 month, with a lot of uncertainties. We have a lot of uncertainties involved, but you must be very careful interpreting your results. You cannot say, okay, we'll have 20% of the population sick in a single day. It's not reliable. Okay, but you can have, I can take 20 days to eliminate the epidemics. Okay, it's just a result of a model. So you can do prediction, but you must be very careful, very careful. I cannot say to you that, okay, if we vaccinated, if the current ratio, you will die 1.5% of the Brazilian population. It's not correct. But you can do very interesting insights about the future of the epidemics, comparing different scenarios. That's the point. You create hypothetical scenarios and compare them. You say, okay, if you vaccinate elders now with this current stage, it will be a disaster, because the epidemic is completely without control. So too many people will get sick and will die and so on. But if you have an epidemic under control, if you use masks, if you take the due distancing measures, okay, you can think you can vaccinate people that are not from the vulnerable, and it could work, but it's very dangerous to trust blindly in models. So we must use the models with a lot of care.
Yeah, I don't know, but I think the major point is that, so it's possible to mention that both you and Americo mentioned that, so that you can define the scenarios, so you can have the best scenario and the worst scenario, and then I can manage to make plans and to control everything. So I think nowadays it's really important to mention that it's possible to define those kinds of scenarios. Then you can develop some analysis that can help. And then, of course, the decision needs to be based on that. And then this is, I think, the point that you can stress for the usual audience in general, because nowadays we are discussing some things that if vaccination is important or not, if the social isolation is important or not. So it's clear that some parameters that you mentioned, so the beta, where you control the social isolation, so the transmission rate, basically, and the vaccination, they are really, really important. So since we are living in a plain Earth nowadays, seems to be that we are living in a plain Earth, so I think it's important to have this kind of idea. And so I would like to ask you to make a final comment about that, if you don't have any other question. So maybe you can close with this kind of
Marcelo, may I add? With mathematical models, you can do qualitative and quantitative analysis. In the context of COVID, quantitative analysis makes sense only for the short term. Any quantitative prediction that you wanted to do with a certain level of reliability should be done in the short-term window, in the short-term horizon, a few days, a few weeks. The behavior, the social behavior plays an extremely important, it's an important player here. If people, because you made a prediction, let's go back to the beginning with the reports from Imperial College. They announced, the reports announced, we're expecting 1.5 million deaths in 6 months. Everybody went in panic. Okay, everybody stay home. This change of behavior changed completely the future, and you have some kind of feedback here. Okay, so forget the utility of the models here is not for the long-term predictions. Mathematical models from the quantitative perspective are not useful in long-term predictions here. They are extremely useful for short-term predictions. Long-term scenarios, qualitative analysis, they are extremely useful. Like you both mentioned, you can design some possible scenarios, more or less median scenarios, or if people behave in this way, or this way, what on average should happen? If we vaccinate in this way, okay? For the major utility of this model is qualitative, much more than quantitative, and quantitative here makes sense only for short-term predictions. I think this is a key message. The one problem, some people put the credibility of the predictions from Imperial College in check because some people without experience in epidemics try to interpret very literally the result and without paying attention in the conditionals. Oh, this will happen if nothing is taken to mitigate the spread of this epidemic. All of this, and other people also interpret an epidemic prediction as 1,500,722. Okay, high fidelity predictions in epidemic you don't have. Okay, when you say 1.5 million, you're estimating the order of magnitude. It's could be around 1 million. Okay, but you should never take it into account as a extremely precise number. Okay, it's an approximation, and it's a raw approximation here. I think this is a message.
Yeah, I would like just to add a comment that there is a lot of people that know the technical part. He could solve equations, he could use the computer to do predictions, but they were not aware how to interpret the results. So some scientists that start to make predictions to release to the media, for example, without the correct care. Said, okay, this is a mathematical prediction, this is a qualitative. You should not look for the numbers in the blind way. Okay, you're trying only to make some ideas about, to predict how many 2 million people dying. It's very complicated because this model assumes that people are like atoms, but people are not like atoms. People are much more complicated. If you have some pronunciation, for example, for some important people like your president, that say, oh, you should not wear mask because they're not important, it have a big impact because people will not wear mask, and people will agglomerate, people will do parties, and this kind of event is very important for epidemics. Even though the models, the simplest model does not take this into account, but they are very important. This horror events. You say, oh, the supporters, the followers of the president are not the majority, but they have contact with many people. So it does not make difference. So to use well the tools that we have, that are the science, is very important, including for the scientists. Scientists sometimes want to do the best. He think that he is doing the best, but sometimes it's not, because you are doing some not very accurate information, and the information can be distorted, and people will say, okay, science is a shit, you cannot do reliable predictions. So you must use the models very carefully, but they can be very useful. Very useful. For example, countries who follow the devices of the epidemiologists, they were able to control the epidemics. For example, Spain were able to control the epidemics, but then they stopped. Okay, the epidemic has passed away, and the scientists said, okay, you should not release the thing now, and then we have a problem again. So even if the predictions are not accurate in numbers, they are very accurate in scenarios, because the scenarios are not new to the epidemiologists, because it is happening in the past, not with this magnitude of importance, but it happened in the past. So you can trust the scientists when they say, okay, if you release everything, if you put kids again in the school, you have a huge increase of the number of infections. Somebody can ask, how many new infections do you have? I cannot say you precisely, but I can say you that it will be a lot of new infections. So it's very important to take care about these points.
I think another important point, Silvio, is the social responsibility of using these models to guide the decision making. You're affecting the life of people, and so you can use the models to orientate your decision, but in order to take the decision, can't be a blinded, oh, the model said this. You have a group of engineers and physicists analyzing this. They are not considering the social part, the medical part, the psychological part. So epidemiology is interdisciplinary and multidisciplinary. In order to interpret the results and take a decision, you need a multidisciplinary team. Yes. You can do your interpretations for yourself, but it's a sense of responsibility. Don't share your thoughts without. Don't share your thoughts, your simulation results in the social network. Discuss it with the experts and see if it makes sense. Because sometimes, my training in mathematics and engineering, I will look a strategy for optimal vaccination. For sure, I will not take a lot of constraints into account that a physician, a psychologist, a social scientist will take care, because I don't have training in that areas, and it's difficult. You don't have one single person with training in all the areas that are necessary. So you need to share your research. You need to discuss it with a group of experts in order to transform these insights driven by the model into responsible public politics. Unfortunately, here we don't see this from the part of the government and from the part of some people with the best intentions of sharing information in the social networks that, in my opinion, give more trouble than help.
No, but I think the models bring more light than some argument that you can see there. Don't worry. So if you don't have, so I don't know if there. I think there is no any further question. So I think it's a good time to close the session. So let me thank you so much, Americo, Cunha, and Silvio Ferreira from the nice presentation. So it's really inspirational. So then you can see, I think, let me say again, I think that you can, both of you, bring some light to this controversial subject that should not be so controversial, but nowadays, yes. I told you, we are living in a plain earth after so many years, so we are back to the plain earth. So thank you very much. And thank you for Aline and the organizing committee for the invitation to be here with those interesting presentations. So thank you very much. And let me return the word to Aline. Thank you, Aline.
So I'd like to thank a lot for the very nice talks and discussions. So thank you, Silvio, Americo, and Marcelo, and also the audience. And so this was the last technical session of the NAMI 2021 webinar series. So remembering that at 4 o'clock we have a short course, and tomorrow we have also the second part of the 2 short courses. Thank you all for the participate of this webinar series.
Okay, thank you.
Thank
It
you
was a
for the
pleasure.
invitation. Thank you for your presence in the talks. Bye-bye.
Bye.
Bye.
Bye-bye.